So in this video, we will understand the first type of controller, that is proportional controller. This is the basic controller. So the block diagram for this controller is KP. This is the block for proportional controller along with the error signal. So here we have reference input. The reference input, I take it as R of S. Then we have the plant. Now for this analysis, I'll consider the first order system. So with the transfer function k divided by 1 plus tau s. This is the simple first order system I have considered for the analysis purpose. Okay. The output is C of S. The input. So we'll consider unity feedback system. With that, plus and this is negative. This is the error signal, and whatever you get here, this is the actuating signal or controlled signal. Controlled, or sometimes it is called as manipulated. And error signal is nothing but the controlled variable. Okay, so with this, first we will consider the closed loop transfer function. So we will derive the closed loop transfer function. Coming to the closed loop transfer function. So C of S divided by R of S is equal to, so when you use the block reduction technique, or when you use different formulas that we have considered in first unit, so the control closed loop transfer function is, this is what we get, kp by kp into k divided by 1 plus kp into k into 1 divided by 1 plus tau divided by 1 plus kp k into s. Now here I'll define a variable or time constant tau dash, which is equal to tau into tau divided by 1 plus kp. So this is the time constant. This is the time constant with controller, with proportional controller, with proportional controller. This is the time constant with proportional controller. So I'll rewrite this. C of S divided by R of S is equal to kp k divided by 1 plus kp into k, 1 divided by 1 plus tau dash s. This is what we get. Okay, so with that, this is the output overall transfer function. So if you want the response, we just if you have to go for unit step response, then we simply have to take R of S is equal to 1 by S, and then we can compute the response of the system. Now, if there is no controller, if the KP block is not there, so what happens is that if you're without controller, just for to understand the difference between two, to compare the two. So without controller, the value of KP will be equal to 1. So you cannot make it 0. If you make it 0, the error signal gets multiplied with 0 and you will not get any control signal. So if when there is no controller, we simply make KP equal to 1. So if that is the case, then C of s divided by R of s is equal to K divided by 1 plus K, 1 plus, sorry, 1 divided by 1 plus, now tau dash is now, I'll take it as tau double dash into S, where tau double dash is equal to tau divided by 1 plus K. Now this is the time constant without proportional controller. Without proportional controller. Fine. So now comparing these two, you can see that the tau dash value is much less compared to tau double dash, because here you can see coming to tau dash 1 plus kpk. So this is obviously greater than 1 plus k. So tau dash will be less than tau double dash. So, so 1 plus kp into k is greater than 1 plus k. Okay. And the tau dash value will be less than tau double dash. So which means that with the proportional controller, with proportional controller, the time response is improved. The time response is improved, because you can see the time constant is much less compared to one system without a proportional controller. So if the time constant is small, we will say that the response of the system, the time response of the system is better. So with proportional controller, we can have better time response than the one without proportional controller. The second thing is that the steady state error. Now the steady state error is very important. This is why we are actually using controller to eliminate or to reduce the steady state error. So if I consider for a unit step input, for a unit step input, okay, so the steady state error is equal to 1 divided by 1 plus limit s tends to 0 g of s into h of s. Now this definition we've seen in the previous sections. Okay, so now first with controller, with controller, g of s is equal to kp into k divided by 1 plus tau s, and h of s is equal to 1. So with that, the steady state value will be equal to 1 divided by 1 plus kp into k. This is with controller. Without controller, without controller, so g of s will be equal to only k divided by 1 plus tau s, and h of s is equal to 1. So the steady state error ESS is equal to 1 divided by 1 plus. So here you can see that, okay, this I'll take it as with proportional controller, and this is without proportional controller. ESSP is with proportional controller and ESS is without proportional controller. So we can see that we can see that with large value of Kp, with large value of Kp. Okay, it is proportional constant. First thing, the steady state error can be reduced. The steady state error can be reduced. So we have this here, with this here, ESS of P is very less, not very less, it is less if compared to ESS. So if you want very less steady state value, so then we can go for large value of K. Similarly, as we've seen in the previous slide, the time response can be improved. The time response can be improved. Though we can have a better, better dynamics and a smaller steady state error, going for very large value of Kp will not be always, it will not be always the advisable, because if you go for large value of Kp, the pole location may get shifted towards the j omega axis and it may reach unstable region. It may reach the right hand side value. So the disadvantage or the limitation of this proportional controller is that it may lead large value of K, but large value of Kp may lead to instability. So your system pole may get shifted towards j omega axis and it may reach right hand side. So it may lead to instability. So whenever we are choosing Kp gain, a compromise has to be done between what should be our error and what should be the stability margin. So these there will always be this compromise whenever we are selecting Kp. So the gain of the controller, yeah, should be selected considering both steady state error and instability. So these two parameters have to be kept in mind. So if more and more the pole shifts towards the j omega axis, the oscillation keeps on increasing. So if we go for large value of Kp, the oscillation keeps on increasing, and sometimes it may go beyond j omega axis. It may reach right hand side of this S plane, and that may lead to unstable control system. So the design of Kp has to be done very uh, uh, precisely, so that we consider always there has to be certain compromise between these two values. So if you want a better stable system, so you have to compromise with the steady state error and time response. And if you require a very low steady state error, then you have to compromise with the stability margin. Thank you.